let's take a look at the warm-up for today. Okay. I'm actually going to do the first one on the warm-up with you, even though I am fairly certain that all of you can do this because you studied this last year. So these systems are easily solved using substitution. We would use substitution when one of the equations is either solved for a variable or easy to solve for a variable. So if we look at this first one, it's already solved for y, so we can take what y is equal to and substitute it in where we see y. So we have 2x plus, instead of the y, we're going to substitute in x plus 4, set that equal to 1. So we get 3x plus 4 equals 1. So 3x equals negative 3. So x equals negative 1. Okay, now that is almost my answer, but it's not the answer because we also need to know why. So we substitute back into that first equation, and you can choose either, but I always go with which one looks the easiest to me. And so I get the y equals 3. Solution is this point, negative 1, 3. And negative 1, 3 works for both equations. A solution to a system must work for both equations. So if we plug in negative 1, we get out 3. If we plug in negative 1 and 3, this is also a true statement. So the solution to a system is an ordered pair, and it works for both of these. All right, there are some crazy things that can happen when we're solving systems. All of our variables can cancel out, and then we have two possibilities for that, and we'll talk about those later on this week. But right now, we're actually solving systems that have solutions, have only one solution. Okay, you try number 2.
I'll do that sheet of paper.
You can write it in your workbook. We're about to work in your workbook on page 97.
97? I'll go to page 97.
Okay.
I do that all of my
Stop, guys!
What did we do wrong?
I'm excited because that leads to my next point.
Oh, so it's totally good.
Okay, let's sum it in a little bit. I am excited that some of you can work this problem in your head, and I can too. Yeah, a lot of us can look at it and go, hey, if x is 2, y is 4, and that works for both of them, 2, 4. And then we don't want to show any work and we don't want to do anything. Okay, but the problem is, am I going to always give you these beautiful, nice little whole number answers? No, I'm not. Sometimes your answer is going to be like 7.125, comma, negative 37.34. Okay?
If it is a decimal, would you like to round it to the nearest hundred?
Okay, that's a good question. She had a question about decimals. I would like you, if it's a decimal that ends, a terminating decimal, like 0.125, one that ends like that. Just write it as a decimal. If it's not a terminating decimal, I'd like you to write it as a fraction, unless we're dealing with a word problem. If it's a word problem, and this is representing a monetary amount, we would round to the nearest hundredths place. So that would be the only time we wouldn't want to give an exact answer, as if it were a word problem. That's not appropriate. Okay, so for this one, if we substitute in what y equals into the second equation, we get this. And 5 times 2 is 10x, and 10x plus 7x is 17x, and then 34 divided by 17 is 2. So those of you that looked at it and automatically knew x was 2 and that y was 4, you are correct. You are. let's make sure we also understand the process of using substitution. 2-4 works for both equations, correct? Okay. If you want, open your books to page 97. Go ahead and do so. Excellent.
You can share mine. The one that I wrote.
Okay. Most of you are bringing everything to class every day, and that's awesome, and I can't catch you by surprise. If you're wondering, if you don't like bringing it all to class, if you open up my website, the newest calendar is there, and you can check that out. If you look at the calendar, it'll tell you which books we're using in class that day. Yes, Kyle?
Yeah, I didn't bring my book because I didn't see, I didn't, like, well.
He didn't
I didn't know, I couldn't access it. I didn't know there was a calendar for me to look at, so I just assumed that there was no.
Okay. Well, okay, that's fine, and you don't have to look at the calendar, but my suggestion is, if you're not looking at the calendar, just bring your book and your workbook, and you can't go wrong.
Yeah.
How about you work on with somebody else today?
Yes, ma'am.
All right, that's so that'll be the thing.
That's.
I normally don't have to in accelerated course because most of you want to do really well, and so y'all will generally make sure you're ready and prepared.
What do
So
you
I bet Kyle will bring his every day he needs it from now on.
Yeah, I will.
I bet he will.
Do you
So,
Normally, on normal days, I check the calendar. If I need it, I'll bring it. If I don't, I don't. So.
I get detention if I have to.
like do you give it for people on a
Only if it becomes an issue.
Okay, I get what you're saying. I think I'm good.
Yeah. Alright, so today we're going to also look at graphing systems, and you guys have already solved systems by graphing. So this is not something new. We're reviewing again, but we're also going to look at it in terms of some application, and that's where we're building in this unit. We're going to this is a short little unit, but we're going to wind it up with a little section on linear programming, which is where we have a real-world application of linear inequalities. And we use that when we're finding an optimal solution for different situations that have multivariables. It's kind of cool. All right, so here it's just defining things we already know. A system of linear equations consists of 2 or more linear equations that have the same variables. Most of the time we use x and y. The solution to the system of any linear equations with 2 variables is an ordered pair. And so we got to make sure we don't just accidentally write down the x, because then I can only give you half credit, because you only gave me half the answer, right?
Yes, ma'am.
Okay, good. That satisfies both the equations in the system. And so one way to check it is when we get the answer quickly in your head, plug it back in and see, does it work for all equations involved? The values of the variables in the ordered pair make each equation in the system true, and that's what we're checking when we plug it back in. All right. So let's look at our first one. Now here we have 2 equations, and we have several different ways of graphing. We know how to graph using slope-intercept. We know how to graph using the x and y intercepts. We know how to graph using point slope. And today we're going to talk about one other way to graph that might help us if they've already established different scales for the axis. All right, so this first one's real simple to put in slope-intercept form, isn't it? All we have to do is move the x over, and we get y equals x plus 3. Pretty quick, wasn't it? So we could come up to 3, plot a point. My slope is 1, so up 1 over 1, up 1 over 1, up 1 over 1. Then I'd pull that ruler out of my, or I'd pull my student ID out of my pocket, or maybe you even have a ruler, or an ID, or something to draw a straight line. So we'll take one of those things and we'll draw a straight line with our straight edge, whatever it might happen to be. Oh, I'm off a little. I'll work on that. Pretty close. Pretty close. I'll change it to green since the dots were green. There we go. Okay, so that's my equation. Now the second one, it's not hard to put in slope-intercept form either. Or we could come down here and find the x and y intercept. Let's do that on this one just to refresh ourselves. If we find the x-intercept, we just plug in 0 for y. So this is what we're thinking about. Probably wouldn't even write it down. Because 2x equals 6 is real easy to solve. What would that be? 3. So our x-intercept is at 3, so we can graph the point 3, 0. And my y-intercept, I plug in 0 for x, so I get y equals 6. So I plot the point 0, 6. And I connect the dots. Or you can do slope-intercept. Up at 6, down 2 over 1, down 2 over 1, down 2 over 1. Oops, and then, not oops, there we go. And it's in the same spot. So we can draw a line now. That's not blue.
How about that?
Still not quite right. And still not blue. Alright, now. Okay, so the solution to the system is the intersection of the points. Because the solution is the point that satisfies both equations. Well, the one point that satisfies both equations is the point that lies on both lines. And the point that lies on both lines is the point at the intersection. The intersection point. Point 41 is the solution to the system. That is not the point 41, that's the point 14. There we go. So that intersection is the solution to the system. Any questions? Pretty simple, huh? Alright, let's flip over then to the next page and look at example 2. They gave us 2 equations here. I want you to choose how you're going to graph these and graph both of these, and let's look at the intersection. Everybody go ahead and work this one. You need a piece of tape?
No, it's gone. The homework is gone.
The homework page is gone?
Yeah.
What are you talking about, bro?
Yeah, bro, I'm here.
101 and 1. Bro, you tripping.
That has never been on.
Did you leave it in here on your desk?
I think I'm.
Yeah, it was found on the ground up here in a general area.
Oh, someone stole it because they lost their book.
I would just stole the book. Seriously.
Well, it does make sense to steal a page.
Not really. Because you're going to miss it the next one.
Okay, don't leave your book in here. Because obviously you lose your homework.
Cade.
Cade.
You should just look at it. You should just look at it. Go figure. Wow.
No,
Or negative 1. Hey, give me your book. No, I just did it. I just did it according to you.
I think it is 4
What?
No, you did not.
Yes, sorry for the algebra and geometry.
Oh my god. Lego movie.
You want to try?
Oh my god.
Okay, so let's take a look at what you got here. Hopefully yours looks similar to mine. Okay, now this didn't intersect perfectly at a crosshairs, did it?
No.
But it was pretty close. It was close to 4, -1.
Yeah,
It's close, but this is more of an estimate. Okay, so it's not an exact answer. What can we do if we want to find that exact intersection? Because
Use the
graphing-
formula.
What
The
formula?
equation. The equation.
You
What
solve
would
the
we do
system
with
of
the
equations.
equations? How would we solve it?
You set them up equal to each other.
How? What did we use in our warm-up?
I love Miles, yeah.
Substitution. Do you see if we took this first equation?
Would it be easier to do multiplication? I think.
Elimination. I'm
Yeah.
gonna talk about that. I'll talk about elimination tomorrow. Okay, so we would use substitution, and we could substitute in for x what x is equivalent to. Because x is also equal to 2 minus 2y, we can do 2 times 2 minus 2y. And so we get 4y minus 3y equal to 12. So you get -7y is equal to 8. And so y is equal to -8/7. Now that's pretty close to -1, isn't it? It's -1 and 1/7. So we were close. Alright, now let's plug back in to find x. Plug in what we just solved for y. Okay, gentlemen, let's make sure we're paying attention. Alright, so we have a denominator of 7 here, so I'll go ahead and rewrite 2 with a denominator of 7, so that's 14/7. And add 16/7 to both sides, so we get 37. So the exact answer would be 37, -8/7. So our estimate was pretty close, because 30 divided by 7 is 4 2/7, so that's pretty close. So we had a nice estimate. And sometimes estimation is enough. Other times we need an exact answer. Alright, let's flip a couple more pages. And we're going to do number 1 at the top of page 102. Alright, Mr. Malone is putting money into his savings account. Account A started with $200 and account B started with $300. Mr. Malone deposits $15 in account A and $10 in account B each month. In how many months will the accounts have the same balance? And what will that balance be? Okay, so we have account A and account B, and what's our independent variable in this situation?
Yeah.
Number of months. Okay, what variable would you like to use for that? Okay.
I was gonna say X, but
Like you didn't say it first. Alright, so if we let M represent number of months, what's our dependent variable?
the account.
Account balance.
Account balance, so the total amount after M months?
B.
Okay. So now I've So now I can set up the system. I have one equation that represents account A and another equation that represents account B. Okay, so the total amount in account A is equivalent to, what was my starting amount? $200. And what is the rate of change? How is this changing each month? $15 per month. Okay, so we put 15 in. And then the equation for B would be 10M plus 300. Okay, let's try to graph this first one. It's got a y-intercept of 200. And they're really nice. They went ahead and gave us a graph, and they figured out the scales, and they titled it, and labeled the horizontal and vertical axis. So we are set. All we have to do is graph it. That is nice. But the way we counted the scales, do you see we're 50s here and 2s there? Which makes counting off a slope of 15 a little tricky, doesn't it?
Ooh, yeah.
Yeah, but I'm.
Okay, let's do intercepts. Well, if we did intercepts, do you see the first thing we do is move that 200 over and we get negative 200 equals 15M? So my x-intercept is negative. It's over here somewhere. Will that work for this graph? No. Well, then let's just pick what we consider to be a nice x value, plug it in, and find another point. Like if I just said, all right, let's do 20 for x and see what the y is. If I plug in 20, do you see I get 15 times 20, 300, plus 200 is 500. So 2,500 is a point. So we graph this one differently because slope intercept really wouldn't work for us because we can't just count out the slopes. The scales are different. We can't actually find both the intercepts on here because they only gave us this part of the graph and they both won't fit. Yes, sir?
Could you just plug in 0 so you know it's always 0?
Well, that's the y-intercept. We already plotted that one.
Oh yeah.
So yeah, that's the other one we do have.
Yeah, yeah.
Okay. Let's graph this. So we're going here. Alright, now you take the same approach and see if you can graph B.
Alright, let's do this. Yes. So 2,300, 500 is also a point on this one, which happens to be where they intersect. So that's my solution. Okay. So they do intersect at the point 2,500. So let's see if we can answer the questions. In how many months will the accounts have the same balance? In 20 months. That's when they are equal. We can look. That's where they are right here. And what will the balance be? At that point, the balance is $500. Okay, does that make sense?
Yes, ma'am.
All right, your homework is out of this Explorations workbook. It is on page 101.
and 102. On 101, you're to do numbers 2 through 5. On 102, you're to do numbers 2 through 6. Okay, go ahead and get start on that, and I'm going to be working on grading your Barbie labs.
Am I one? You should be the version.
Yes. I remember one time